Okay, so today's lecture will be given by Sudarshan Vijay. Sudarshan did his PhD at the DTU in Denmark, working on catalytic properties. Then he moved for a postdoc in Persons group at the Materials Project, where he delved into machine learning properties. And then last year he joined a VASP software company, and he works on interfacing VASP with Python codes and also improving calculating catalytic properties with VASP. And today, Sudarshan will focus on different strategies that you can use to optimize the structure of a system. Sudarshan, take the stage.
Cool. Thanks, Martin. So today the idea is basically just to delve a little deeper than what we normally would in terms of understanding what structure optimization is. This word might be alien to some of you, so we'll sort of delve a little bit into what this means, what we expect in terms of input, what we expect in terms of output, what you can do with the output of these things in some degree. So the first part of the presentation will be about determining what this is. The second part will be about looking at the kind of quantities that we need to do the things that we hope to do. And finally, towards the very end, we'll start to sort of look a little bit at how this can be applied to some of the few problems that we may be interested in. So let's start at the very basic. So the questions that a lot of people in material science, chemistry, or otherwise want to sort of investigate are those of material properties. So I think these are a couple of common questions that I typically come across. This typically involves the idea that you want to study the ground state properties of some sort of phase or otherwise of a certain material. This is fairly common these days in terms of using computational methods to characterize and understand certain materials. I think a relatively common extension of this is to sort of understand what surfaces are, what they look like, why something restructures, why something doesn't, or why a certain material is more suitable for something than another, particularly maybe battery materials or otherwise. And so all of these questions are, while they are diverse in scope, I think they ask kind of the same question in a fundamental sense. If you have a certain composition, so if you have a certain stoichiometry of something, say, for example, you have iridium oxides, you know sort of what the stoichiometry of iridium and oxygen is, and you sort of know from experiments, or you have perhaps a guess, some papers from a while ago that hypothesize what the crystal structure is. So you know some sort of idea about the composition and something about the crystal structure. You hope that you can basically figure out what the ground state structure is. So basically what structure would predominate, all things considered equal at thermodynamic equilibrium. So this is sort of, I guess, what a lot of us in the last couple of decades or so in terms of practical speak have been investigating. And through this lecture, we'll sort of investigate how to go from this question to begin to deal with how to answer some of these questions using the tools that we have and the inputs that we are given. That's what's going to be the scope of this entire lecture. So let's formalize it a bit in terms of what we're going to look at. The first thing is what quantities do we need to be able to transform something from like a composition in a lattice to something that's a ground state structure. So how do we even think about some of these things? How do we obtain these quantities? So what does this mean when we say that we want a quantity? How do we get it? In particular, how do we use VASP to get some of these quantities? This is going to be the outcome of this section. Finally, I think this is perhaps the heart of the topic, is how do we use these quantities to get to the ground state structure? So what are the algorithms that take us from one structure to another? And in particular, I will stress a little bit as to how VASP is using some of these algorithms. So some of the intricacies or quirks of how some of these algorithms work and how to tweak and tune them. And then very briefly at the very end, I'll talk a few practical aspects of working with these, some of the aspects that one should keep in mind while using some of these algorithms for their own work. So this is more of a practical use case of some of our methods. So with that, let's begin. Let's contextualize the problem even further now. So let's look at fair schematic of what a lot of our problems will look like. So on the y-axis, so on the axis that goes in terms of the color, you have the energy. So red, most of this presentation is going to be unstable. Blue is going to be stable in VASP and pretty much anything else with DFT. A more negative energy typically implies stability. So if in this valley or in this valley, for example, or if you're in this peak, you are highly unstable, whereas here you are fairly stable. So this is what most people would call a potential energy surface. So you have a surface which based on your positions of your species and your lattice. So basically based on the arrangement of atoms that you have in some sort of crystalline system, would give you either a very high energy structure. So you see, I have made a sort of purposefully what intuitively looks like a very high energy structure. Their atoms are fairly close by. They are organized in a fairly random way. One would intuitively think and perhaps guess that you have a very high energy structure that's determined here, something that's not very stable. So high energy, very unstable. And you'd like, of course, to go to something which is a low energy structure, something that's particularly stable. So that's denoted by these two black points. And you basically want to traverse the potential energy surface. That's the x-axis in this scenario. And you want to see how you go from here to here. That's the root of this entire lecture. So this entire lecture is basically how do you go from here to here and how do you do it in a straightforward. So how do we begin to think about going from here to here? So, well, firstly, we need to know where we are in terms of these quantities. I think a basic understanding of calculus here would be particularly useful in that. So if you are at a certain point and you'd like to sort of change your position, so you'd like to go in this direction, you basically need to know the derivative of the energy with either the position or how the lattice changes. So it's typically called the strain tensor, but basically how the lattice changes. So you're primarily interested in how the energy, so the y-axis changes with x and a in some degree. And if you know that, at least you know which directions to take in order to go from a very high energy surface to very low energy one. So the good news for us, of course, is that DFT sort of gives you pretty much everything you need in this scope. So I will show you in the next few slides that one of the good things about DFT is computing this derivative, the derivative of the energy with the position, or its negative is particularly straightforward. So it's what you'd call the force. A classical analog to this is basically the change of the potential energy with position is typically given as a force. So this is, you could think of it as the same way. This is your atom-centered forces, as it is sometimes referred to, as given by arrows in this schematic for a random collection of atoms. And the second quantity that we will meet perhaps only briefly in this discussion is the stress tensor. So how the energy changes with how much you change your lattice vectors. And that, of course, determines how close your atoms are to each other because your lattice vectors govern your positions. So the next 4 or 5 slides or so will basically delve a little bit into how the forces are computed and how this applies for the stress tensor and what these quantities mean in the DFT context. So let's get into that. The first and perhaps the most intuitive thing when it comes to determining forces, I guess this is something that we all think about is, well, okay, we need the forces, so we need the derivative of the energy with the positions. Let's just move the atoms by a tiny bit in x and then compute the energy and then determine the force. This is the naive and perhaps intuitive way of thinking about forces. Well, this is particularly expensive for even moderately sized systems. You could think about it this way: if you have a crystal structure of some sort and you need to move an atom in position X, then position Y, and then position Z, and you need to do it again for another atom, it just gets cumbersome, right? So it just increases with the number of atoms that you have. And even for realistically moderate systems, this is an untenable situation in terms of computing these forces with finite difference. So this problem was solved actually quite a while ago, 80 odd years ago, if you look at some of the original papers, and of course adapted now to our context, in that you can get these forces. So the force at a certain atom center, you could get this analytically. And we're going to go through a very sort of surface level understanding of this, but hopefully enough that you understand it in a practical context when you actually see these quantities in a VASP output file. So we need to compute these quantities. We want to do it analytically. We don't want to do these finite difference things. So how do we go about it? Recall either from early lectures or otherwise that the wave functions that we're going to be looking at are basically split into ion and electron wave functions separately. We assume that the ions move very slowly in terms of how the electrons move. So this is typically referred to as this Born-Oppenheimer approximation. And this basically leads to what's essentially an energy equation, a Hamiltonian, that gives you an expression for how the electrons and ions behave in this approximation. Let's put it that way. Let's briefly look at what these terms mean. This is the kinetic energy term, let's put it this way, and we'll come back to this. Then you have the ion-electron interactions. Again, we'll come back to this. Then you have the electron-electron interactions, and this might be familiar to some of you as just being interactions at a hearty level. So basically, you have just the interaction of the charge density with the other charge density in R prime. So basically, this is also fairly straightforward. From previous lectures, you've heard about the exchange correlation energy. So this is also an energy. And finally, you have an ion-ion interaction. So this is also something that we will come to in a second. So we are interested in the change in the force, or change in the energy rather, with positions. So when we look at this expression, I think it's fairly important to see what changes with position, in particular the ion position, because that's what we're interested in. What you basically see is that the kinetic energy operator doesn't really change with ion position. So this is not particularly useful for this discussion. This is purely dependent on electrons. So well, this will not change either. In most cases, the exchange correlation also does not change. So you sort of kind of ignore that for now. And you're left with basically two terms, right? You're left with the interaction of the ion and electron, and you're left with the ion and ion interaction. And that's pretty much it. And so if you take these terms, essentially, so you have now the Hamiltonian, and now you want the derivative of the energy. So we start by looking at just the energy. Recall, this is how you would get the energy if you have a certain Hamiltonian H. You basically perform these manipulations, and what you end up with is, and of course take the gradient, is something that looks like this. So let's contextualize this a little bit. You have an integral over all of the charge density, so the electronic charge density, and the derivative of the external potential. So that's something that looks like this. And you have another term, which is the derivative of the energy with the potential. So you have two terms. You have one which just looks like the derivative, and the other which is an integral over the charge density and the derivative of the potential. I will say that this is, we'll come to in the next couple of slides, the easiest term to perhaps compute in all contexts, because it's purely classical. It's the interaction of the ion and another ion. So these are point charge interactions. There are very many different methods to compute them. VASP implements one particular one. And essentially the idea is to compute these ion-ion energies and take the derivatives with positions. So this one is fairly straightforward. This one is perhaps the one that you require an electronic structure code for, because you need this so-called external potential. In VASP, because it's a sort of pseudo-potential code that's plane wave, you need a few different potentials. You need the ion potential, which is treated like a point charge, sort of, and we'll see what that looks like on the next slide. You then have the local pseudo-potential, which is also a potential contribution. So you'll see how these sum up. And then you have the non-local pseudo-potential. And this basically comes from the fact that the wave functions depend implicitly on the ion positions in a pseudo-potential code. This is a relatively minor contribution as compared to these two. So we will sort of not talk a whole lot about this in this lecture, but it's important to realize that there are three different potential contributions that go into the computation of the forces. Okay, so to summarize, you have different potential contributions. You need to take their gradients with ion position. That gives you the first term. And the second term is just the ion-ion positions. You will see this referred to in many places as the force theorem. Often people refer to this as the Hellmann-Feynman theorem. They're referring to some part or all parts of this basic expression. So let's dive into a little bit of what these individual contributions mean, at least at the surface level. So this is what the local force is going to look like. So as I said, again, you take this familiar integral, you have the charge density, and you have the derivative of the potential with the positions. I ran a very simple calculation just to sort of illustrate this. This is for some charge density, you have here the position of oxygen. So two oxygens in a cell, or rather an oxygen molecule in a fairly large cell, and it's basically averaged over the z-axis. And what you see is that the local pseudo-potential looks kind of short range. It looks kind of very narrow peaked at the ion positions, something that looks like this. And then you have the ion positions itself, which look fairly broad. It seems to grow outwards as you move through the cell. This is what the ion position sort of looks like. And that's pretty much it. So if you have these expressions, you could basically toss them in here, compute their gradients, take a dot product, and sum over. And then you have the force. It's as simple as that. This would be a little bit cumbersome in real space. So in terms of R, the easy way to do this is basically to move to G. So not look at it in terms of R, but look in terms of G, so reciprocal space. And then this is again a fairly straightforward manipulation where the integral becomes the sum, the derivative comes with IG times the exponent, and then the sums themselves are just Fourier transform from reciprocal space or real space to reciprocal space. And that's it. You have your local force, and it's really as straightforward as just determining the potentials. A quick note on the ion-ion potentials. I mentioned a couple of slides ago that this is a purely classical contribution. It is, and as you see some of the papers cited here, it's a long ago classical contribution. But very briefly and very qualitatively, just to sort of understand what happens here, we are interested in the interaction of one ion, let's say the ion in red, with all other ions that are nearby. We're typically looking at a crystal, which is a sort of infinitely repeated periodic replica of each other. And so this sum becomes very, very difficult to compute and is only conditionally convergent in most cases. So what was determined is essentially if you split your calculation of the energy into a real space part, which is basically determined locally to some cutoff, and the reciprocal space part, which takes care of everything else, the sum is much easier to compute. And that's essentially what's shown here. At a very surface level, you can sort of look at Q1, Q2 by R, which should remind you a little bit of sort of Coulomb interaction, along with some sort of error function or complementary error function like behavior, which cuts it off. This is the real space component of this summation. And the rest of this is basically just a reciprocal space component of the summation, which is basically just treating how this ion interacts with all other ions. And this is done with this sort of quote unquote competing charge, which we will not get into. But the essential idea is that you can split the interaction between an ion and all its other ions into two parts and then take the sum together. And once you have this energy, it's fairly trivial to take its derivative or gradient. These are analytical sums, so these should be fairly easy to compute. And once you're there, you have the force and you're good to go. Essentially, you have all the contributions of the forces. A practical note here that you can take all of these forces, look at them and visualize them and try to see what's really happening. We have a tool developed in-house, which is applied for VASP. Some of you might have come across it already. If not, highly recommend you give it a try. The idea is basically you can open what's a Python interpreter throughout this presentation. If you see these two greater than signs, I guess, you're basically in a Python terminal. And so basically you take your calculation and then, for example, you can print the force and it looks sort of like this for two oxygens. So sort of what it looks like. And the forces are of course opposite and equal to each other. So this is what you would expect from something that looks like this. So somewhat easy and straightforward to do. You can also read out the forces in terms of post processing. I'll not go into this a whole lot, but highly recommend you check out the tool and then the associated docs. You can also plot it, which is another nice feature, I guess. You could plot things and look at how stuff works. It's always nice. You can also look at the different components in the outcard file of the different force components that I mentioned in the last couple of slides. Okay, cool. So forces hopefully are clear. I think it's a small step in terms of at least a qualitative understanding to go from forces to the next step, which is stress. And why do I say that? Well, if you look at sort of the structure here, you have energy is something you can compute. If qualitatively or at least analytically, if you move a position of an atom from one place to another, you're going in the direction of a force. So how the energy changes with positions is essentially the force. The stress is much the same, except you're not changing one position, you're changing all positions. So you can picture this cell as being slightly larger than this cell, hopefully. And basically what's happening is your cell is basically expanding, right? So you have a larger or smaller cell. And that should qualitatively at least ring a bell that you have a stress tensor. So first, if you're just moving single positions or interested in positions of one, it's a force. If you're interested in the lattice vector moving and hence the position of all your species, then it's the stress tensor. And as you may imagine, it's perhaps a bit more complex. The forces are X, Y, Z, but this is a 3x3 matrix essentially composed of 9 elements or 6 that are because it's symmetric. And we'll get to sort of what this means in a bit. But hopefully it's self-evident that we can compute energy, we can compute a force, and we can compute a stress tensor, and the stress tensor is just one step beyond what we spoke about in terms of computing the force. Let's sort of summarize what we have. Perhaps the only thing you should take away is that the gradients of the energy with positions and atoms are given by the force and stress tensor. This is something to keep in mind. Perhaps the caveat or the corollary to this would be that these are fairly easily computed with DFT. So if you know what you're doing here, you should be able to compute it with DFT in a fairly easy. Cool. So let's go back to our outline. We know what we need. We need forces and stress tensors. How do we do it? We do it with DFT. Let's go now to the meat of the matter. And how do we use these quantities to essentially compute the ground state structure? So given a certain force and stress, how do we proceed towards a stable structure? It's no point having just the force and stress of a certain structure. We need to do some work. We need to move in a certain direction. So that's what we're going to discuss now in terms of all of the algorithms that you'll be seeing. So let's again contextualize the problem with the same figure. So again, you have a potential energy surface. The red point is unstable. The blue is stable. We need to go from this high energy structure, which looks somewhat unstable, to a low energy structure which looks fairly stable and symmetric and so on. So we want to sort of go along a path that takes us there. If you have a certain point here, I think two questions come to mind intuitively. Which direction should I go to descend down this path such that I reach this point? And how far do I take a step? So how do I need to sort of jump here, reevaluate, jump here, reevaluate, or can I do it all in one shot? I think these are sort of the key questions that one should answer, at least contextually, before moving on to the different algorithms. Let's start by answering which direction should I descend. I think that intuitively you will see that this is related to the force, essentially from this next discussion. So let's start very simple, in a very toy model. Let's say you have a function which looks like this. It's a function with a minima that's clearly at 0, 0. So it's a function that looks like this. And if you go in any other direction, you're basically increasing the value of your function h of x. This is what it looks like. H of x looks like this. If you ignore the vectors for a moment, it looks like a quadratic equation, right? You have x, and then you have just x, and you have nothing after that. So that's sort of what this looks like. This gives you a function. So you have, at each point, you can put in a value of x1 and x2, which is essentially just a vector that goes in here into x, and then you compute all of these different quantities and you get out hx. So this is the function that we'll be playing around with. It's a toy function. So if it's a stationary point, that is, let's consider here just a minima. So if you are at 0, 0, so at exactly this point, bx0, that is the derivative of h of x, is basically 0. So there's nothing changing when you're at the minima. This is the definition of a stationary point. And this is what we want to get. So we want to get x0. So this is our approach, right? So if we are somewhere here, we want to go towards the minimum. This is something that we'd like to do. Let's rephrase all of hx in terms of x0. So basically you're just subtracting the stationary point from this. It's just a bit of manipulation. And then we impose two constraints essentially on what this matrix A can be. We say that all eigenvalues of A must be positive. So you may hear this as it being positive definite. It's essentially what this means. And less important for this discussion, but also a requirement, is that A must be its transpose, which means it must be symmetric. So if you impose these two relatively straightforward conditions and take the gradient of h prime x, or take the gradient of hx, so h prime x, you get something that looks like this. And all you need to do is then invert your matrix, you get something that looks like this. This is actually a fairly useful equation, and perhaps a lot of what the next part of the lecture is based on. And its power comes from looking at what it has given us. So it has given us the fact that you can compute the minimum, so x0, which is the minimum position that we're after, for any position x. So if you are at any point x in space, anywhere in this graph, you can basically compute x0 if you knew what A is, if you could invert A, and if you knew the gradient at the position that you were at. That's pretty much it. So if you just knew which position you were at, you could basically compute everything and the problem would be solved. So this is, of course, a generic expression. Let's look at it in terms of DFT, or the energies and forces in terms of atomistic simulations, essentially. And this will bring us to our first algorithm, which is steepest descent. So how does this very simple frame of reference deal with us? The energy, you can express it as this expression here. So you have the H, which is going to be called the Hessian, which is basically the second derivative of the energy with positions. And you have the forces, which is the first derivative of the energy with positions. And so you basically, you could express your energy at least approximately in this form, where you have the Hessian and the forces and a reference point, basically an energy at a certain point. You could then basically write the same expression that you saw before, where you are hoping for the ground state structure, the minimum structure, where all the forces are 0, and you have x at a certain point, and you want to invert the Hessian, and you want to just take its product with the force. So you basically want to do something that looks like this. And that's it. That's steepest descent. It's not a whole lot more to say about steepest descent. Fairly simple algorithm. The problem is that in most real world cases, it will struggle to find a minimum. I think the reasons for these are fairly obvious, in that if, for example, you had a potential energy surface that is nice and quadratic and the Hessian is known, it will solve instantly, it will converge instantly. However, I think it's really premature to expect this of real world cases. Most potential surfaces don't look like this. They actually look perhaps even more complicated than this. This is even simpler than what most things look like. So things are pretty complicated in the real world. So you see something that looks like this. And of course, computing the Hessian is very expensive. So it's not something that one can do trivially and in a most easy way. So while intuitive and simple, this algorithm is not something that we can use in a practical sense pretty much ever. So let's look at the algorithm and how to activate it in VASP and how this is actually implemented in some sense. And you'll see a lot of these algorithm blocks in the next slides. This is basically to illustrate and to summarize what we saw in terms of figures. So if you given your positions at a certain iteration number I, if you given your energies at a certain iteration number I, and if you have your forces also at I, and lattice vectors A, you will output the next positions and in their associated lattice vectors by steepest descent. If your forces are greater than a certain threshold, so are not converged yet, if it's lower than a certain threshold, you are converged, then essentially your next position will basically come as a sum over your previous position, some factor, and your force. So it's really as simple as that. Your positions are largely controlled by the force. VASP in particular uses the mass normalized force. This is largely to prevent very, very small atoms from moving very quickly with large forces. So this seems to work very well if you were considering a very simple scenario. Choices for lambda typically are given by the eigenvalues of the Hessian. So if you compute the Hessian once initially and take its largest value, or 1 divided by the largest value, this might be a reasonable guess. But in general, I would say this is not really usable in the real world. It is a simple method. It is good for comparison. It is good for playing around, but I'm not sure it's useful for the modern day relaxation process. It is possible to do with VASP. I illustrate some of the in-car tags that you need. You need to set I benign is equal to 3. You need to set S mass is 2, and we'll talk a little bit more about S mass in the coming slides. You need to set potem, which is the value of lambda here. And E diff G is basically a threshold that you need for the forces. So something that looks, we'll come to what the exact numerical value should be, but this is the tag that you need to look at. Great. Okay. So simple algorithm, we got that out of the way. Let's see how we can improve it. And the easy way to improve it is with these quasi-Newton methods, so to speak. They are called RMM dice or DIS. I will stick to either quasi-Newton or dice separately in this talk, but they refer to the same thing, at least in the course that we develop. And the algorithm is again very simple, but it uses a little bit more information than steepest descent. So what we say is that if we are sufficiently close to the minima, so if we are not at the minima, but we are somewhere there or thereabouts, we can use information from previous steps that we have performed to better inform our next step. So let's look at a very, very simple example, perhaps even one where you don't really need quasi-Newton methods to converge, but this is fairly illustrative. So say you have a structure that looks like this, and you have an atom that's placed here. This, of course, looks out of place. And then the force basically takes the atom in this direction. So it wants to move the atom along this direction. So we do know how much to move the atoms by, but we don't really know how much, right? We can move it 1, but we're not so sure. So we know the positions for this particular case. So that's fine. We do steepest descent. That's okay. And then after doing steepest descent, essentially we have another atom position. So we have something that looks like this. And then we compute the forces for this, and we get something that looks fairly reasonable. Well, we could do steepest descent again and then hope it works. But an easier way of doing this is basically to use the information from here, which is the force evaluated here, and here, which is the force evaluated in the first step, and sum them together in a linear combination of ways such that they're coefficients for linear combination. So basically you can determine this F opt, which is this optimal force, I guess, as a sum over alpha, which is the number, for a certain I, a scalar, for the force that you have here. So all of the forces will basically just be summed over in this manner. And you minimize this under the conditions. So you minimize your gradients, you minimize your force under the conditions that sum over all alpha is. So in summary, you are using information not just from the force that you have here, but you have information from the forces before, the information from the forces in steps before, and the positions and the energies that have come before. So you essentially have more information that you've provided your algorithm in the hopes that it finds something a little faster. Let's look at this in a more contextual sense. So you have, again, your positions, you have your forces, and you have your cell vectors. And the output from this is basically the next position. Again, you would want your forces to be greater than the threshold. Do any of this. If it's not, then stop. The first iteration that you do, because you don't have any previous steps in the first iteration, you need to start somewhere. You do steepest descent. So you basically just move your positions along the negative of the gradient, which is the force, So you just move your positions in this way, and this is just steepest descent. If not, so if you're not in the first iteration, then I write here in a vague sense, and we'll talk about this briefly in a moment. You have to decide I, which is the number of structures to keep in memory. So you don't need just a certain number of structures in memory. You basically have to decide this, and we'll come to how we decide this in a second. But say you decided, so say you have a number, say 2, for example. You then determine alpha I based on this optimized force, which is basically sum over all of the alphas and force. You then use this alpha to basically determine an optimal position. So something that looks like this is the same expression, just with replacing force and position, under the constraint that the sum over alphas is 1. So both of this is performed with sum over alphas 1, and this is basically just used as an expression. And finally, your next positions are given by a sum over the optimal position and the optimal force with this lambda constraint. You can sort of think of the steepest descent and this expression to be very similar, apart from the fact that the force at that position, it's a force which takes into account all of the previous forces that you've used. And a position that's not just the position now, but a position that takes place, uses all of the information from the previous positions that you've traversed, or a few of them at least, not all. And this gives you the next position. So how do you activate this with VASP? Fairly similar. You have I Brian as 1, simple, easy to remember. 1 being the first algorithm. You need a certain totem for at least the choice of steepest descent, so lambda. N free is the number of steps to be kept in memory. So I mentioned in step 5 of the algorithm that you need to decide I, which is the number of structures to keep in memory. Make sure that you choose something that looks reasonable, and we'll come to what a reasonable value is in the next slide. And you need EFG, which is the force threshold. So what you consider to be converged. I think these are the 4 important tags for this algorithm. Let's visualize this through a very simple function before we jump into some of the more heavier materials or methods. This is DICE, the quasi-Newton method with I prime 1. I've taken 3 steps essentially, so to illustrate what the algorithm is going to do. Say you start here, which is where my red cursor is over the red point. 0.6, 0.5. The first step is along these lines. So the arrows along all of these figures is basically the force, and the absolute value. So the color is basically the position. So you basically want to go here. This is the minima, right? So if you start here, you basically want to go here. So if you start here, like this is the positions, it takes a small step. So it takes steepest descent initially. And now it recognizes that it has the force here and it has the force here. So it sums them together, forms an optimization to find the minimum force. That's probably somewhere around here. It gets the optimal positions, which is also somewhere around here, and then jumps here to sort of a place which is on the path towards the minima structure. So this is quite nice, right? So you do steepest descent once, and then you get another structure which is pointing, at least orienting to the minima essentially, which is going to jump around here. And then the algorithm continues depending on the step size that you have and all of the different sort of parameters that you have in the model. But briefly, this is these 3 points at least hopefully illustrate the intent of the algorithm. So what the algorithm is trying to do in context. Something to note is I've started fairly close to the minima. You may argue in some degree. The performance very far away from the minima may not be as nice, especially if your forces are not, or if your forces start to increase somewhere along. So you have a valley and a trough. This method will fail. So keep in mind, really start this only for things where structures are not terribly awful. This is something which will work only if you're there or thereabouts. This is the best place to use this method. A note, so things to watch out for with DICE. Note that n free can only be as many as the degrees of freedom that you have in your system. In the absence of any symmetry, this is 3 into n ions minus 1. Why minus 1? Well, because you have translational symmetry. So the idea is basically one atom is independent and everything else depends on that atom. And 3 because you have 3 positions, x, y, and z. So make sure that it's lesser than. In general, if you have symmetry, this is harder problem to determine. You can look at the outcar file and you can basically see what's used, but this is something to be kept in mind. I think what most of us do is basically we don't set it and we let VASP determine it internally. This is perhaps the more commonly used way of dealing with n free. So if n free is not set, the algorithm, that is RMM DICE, will automatically decide all of the previous iterations. And how it does this is essentially through looking at this B matrix, which is basically the dot product of your forces. As I mentioned, it needs to decide the optimal force. So it needs to do this in a way that optimizes these coefficients under the constraint that lambda is 1. So remember, we're doing a dot product between this matrix and this. This conceptually can be thought of as a way where the dot product is performed with the coefficients under the constraint that lambda, which is the Lagrange constraint, is set to 1. Or the sum of these is set to 1. This is what the constraint ensures. And then you perform this matrix inversion and you determine alpha. A good heuristic to remember is VASP determines N3, but it determines it in a way based on what this matrix or the inverse of this matrix and its associated eigenvalues look like. So you can see this in the outcard file. So you can see that this is it writes out something called Brian in the std out, which given by the norm of the forces will be given here and the norm of the stress will be given here, just to give you an indication of where you are. And then it will tell you how many eigenvectors or how many eigenvalues it will retain, how many steps prior it will retain. So in this case, it says it will retain 3 steps with a mean eigenvalue of 0.87, and it will report all of the eigenvalues that it has. Ideally, you want something which is not too large. For example, in VASP, if it's greater than 8, it will basically throw away all of the previous values and start again. So it will delete its history, clear the history, and then start again. This is a heuristic that's determined from a lot of testing. So this is what VASP does. And the eigenvalues are basically reported in the std out file. So take a look at these, make sure that they're not super large. Otherwise, you're probably drifting through something where you don't want to go. It's a good heuristic to check whether things are working out as they should. The other thing to consider, and some of the eagle-eyed participants of this workshop may have already noticed, that no energies were considered in this algorithm. So all of the inputs are just the positions, the forces, and the lattice vectors. So there's no energies. And so if your forces, which are the ab initio quantity that is being received by this algorithm, are no good, the method is not going to work. So garbage in, garbage out. If the force is bad, the method will not work. So do make sure that your forces are converged well. I'll talk about what this means in a second, but something to sort of really recognize with DICE is that you have to be fairly close to the minima, and the fact that your forces have to be converged, because we don't use the energies in this method. How would you ensure that your forces are converged? You'd use this ediff tag. Ediff is the energy convergence of the previous SCF step. So you have to make sure that your energies in your SCF step prior are well converged. This will lead to a good force that you will supply to your algorithm. So ediff controls energies. If it's a very tight energy cutoff, you basically tend to get better forces. And as you get better forces, you can use your method in a nicer way. So just to illustrate this, I have a simple example of beryllium oxide. Start with a very sort of almost negligibly small ediff. It takes 19 steps to converge. This doesn't even converge. You could even argue that this convergence was fortuitous. And then if you keep on increasing your ediffs, you do more and more convergence tests, you basically get to a point where the energies are stable and the number of steps that it takes are stable. So the forces get better, but they don't really matter. You converge in 10 steps. You can do similar analyses for your test system just to study it prior to running a lot of DMT calculations. Great. So we've done RMM. Let's go to something which is a bit easier to use, at least in context, and that's the method of conjugate gradient. This is the third algorithm. We've done steepest descent, we've done DICE, and now we will do conjugate gradient. So the idea behind conjugate gradient is novel. It's fairly simple as well, in that if you have an initial structure which is sort of given like this, and say you have some forces on the ions given as this and this, you basically want to take a step in a direction. So you want to basically take your atoms and move them in a direction only once in that direction. So you don't want to basically take a step here, say where my cursor is for the green atom, take a step here for where the cursor is for the yellow atom, and then do something else and then come back and take a step in the same direction. This is a waste, right? So if you take a direction, take a step in a direction, you want to take that step in that direction only once. That direction should never be called again. And that's what the conjugate gradient algorithm does. Essentially, when you take a step here, it basically puts your atoms here, essentially, and then you have a new direction, new search direction, everything is new. So the base for conjugate gradient, not just in electronic structure calculations, but more broadly, is to take the direction only once. That's the idea. So how is it visualized in context? Well, you have something that looks like this. You have the energies basically move in. So say you start from here, you move a little bit with steepest descent with some sort of mass normalized way. And then you see that the search direction is completely different. It's orthogonal. You're almost very close to the minima in this case. In this very simple example, I must caveat, the conjugate gradient basically jumps here and then jumps to another direction. And at least in this simple function, you can basically see that your search directions are orthogonal, essentially, almost. And that's the way you want it to be, ideally. So the way you've moved your atoms is completely in a new direction, and that's what you want to do. You want to explore one direction only once, and you want to keep moving in the direction that gets you closest to the minimum. Let's see what the algorithm looks like. So here you have positions as an input, you have energies as an input as well. So note, in comparison to RMM dice, the energies are used here. You have the forces and you have the lattice vectors, and the output for these things are basically your positions. So xi plus 1. If your forces are smaller than the threshold, so something that looks like this, the algorithm will stop. If it's greater than the threshold, it will check if it's the first direction. If it's the first direction, then essentially what you need to do is you need to do steepest descent. Again, you're very familiar with this equation already. This is steepest descent. And the next step is basically just assigning di, which is the directions, to the force. So force negative of the gradient is set as the direction. And this is just the first iteration in terms of steepest descent. Once you're back for the next step, what it does is it takes the directions that you had before. So it has the force in the previous direction, or rather here, should I say, the force in the previous direction and the force in the current direction, and it determines this quantity beta. This beta is basically passed into the previous search direction and the current force to give you a new direction. So as I mentioned in the previous slides, you want a new direction, you want a direction that's different from what you've chosen before. These two algorithm blocks essentially ensure this, that you make your directions different. You then need to perform, so now we know the direction in which to move, we don't know how much to move it by. This is performed with essentially line search, and we'll get to what line search is in a minute. And if you know how much to move, which is this quantity alpha, then your positions basically move in a way that your alpha is just a product of the quantity that you need to move it by times the direction you need to move it by. And then you have new positions. And it's really not a whole lot more different than this. You have an ability to set your direction given by this term here, and you have an ability to determine how much you need to go by this term. And these are the two levers essentially that conjugate gradient tunes. How do you set this in VASP? Well, you do I' 2. This is the base key for switching on conjugate gradient. There are a couple of levers to tune, particularly potem, which is just lambda. So in this step, how do you move? This is given by potem. And then you have E_diff_G, which is the force threshold. So this is whether your algorithm has converged to the degree that you would like. I will say, and I'll keep saying this at least once more in the presentation, if you do not want to tinker with any parameters, if you just want to get something that runs, this is your method. It may not get you there in the fewest amount of steps, but it's fairly autonomous unless it's sort of you have some very, very strange setting of potem. But this is sort of the way to go if you're studying systems where you cannot afford to tinker with parameters. So keeping this in mind, let's understand a little bit what line search is. So I spoke about alpha, and I kind of brushed it away saying that alpha comes from line search. Let's visualize what line search is, and this will help you understand the output from the program in sort of diagnosing if something doesn't go right. So what does line search mean? So say you have a function which is given in black here, and you have 3 points essentially for those functions. So you've evaluated the function and its derivative at 3 points. So you have 3 points, you know h of x at that point. H of x is the y-axis, x is the x-axis. You know where these positions are, and you know their gradients, which is given by, well, the negative of the gradients, which is the forces, which is given by the blue points. So you know everything that you can about these points. What does line search mean in the most simplest context? Simplest context would be just to fit this green point over all of these positions. So you know their positions, you know their derivatives. So you can fit a nice spline of some sort. You can take this spline and determine what the minima of this spline will be, which I think is somewhere around here. And then you perform a DFT calculation on this, and then you determine what the minima is, or something that looks like this. If this green point is very different from what you determined prior, you have trouble because your algorithm is not really working so well. It's not really a cubic spline. But if it is fairly close, that something like this, you're in good shape, because now you have a completely new point in which to look at. And then you can drive this point towards the true minima as you go along. And that's sort of the idea behind line search at a very sort of heuristic sense. what VASP does is not terribly different from this. It is perhaps more complex, but it is hoping to achieve something that looks very similar. So the first step is what's called a trial step. It's basically steepest descent with the chosen totem, which we've seen before. The next step of the trial step, so still called the trial step in VASP, but it's essentially this, is to determine the minima of this green function, which is first determined. So you have a green function which is determined as a cubic and or quadratic interpolation using all available quantities, so the point positions themselves, the black points, and the blue points, the forces. And so you have both of these things. You can determine the green curve and you can determine the green point. And then you perform a corrector step. So you check whether your values are close to what they were predicted by the interpolation. If they are good enough, stop, go to the next step, and go back to step one and take the next step and trial step and continue. Otherwise, it uses what's called Brent's algorithm. I do not have the time to go through this, but this is something that you can look up in any good reference. And this basically helps you improve things beyond this green line. So it uses bracketing and proceeding through to find you a better estimate of the minimum. It's a little bit more expensive, but nothing compared to a DFT calculation in most cases. So this is sort of the algorithm that's implemented in VASP. So a sequence of trial steps and then a corrector step. Trial step and a corrector step, a trial step and a corrector step. That's how the conjugate gradient algorithm is basically proceeding. So now we know what this trial and corrector step is. Let's go and look a little bit at what is used in VASP. So what are the outputs looking like? I'm going to highlight a few of the outputs. There are several, but I think there are some things you need to keep in mind if, for example, your code is not converging. What should you look at? So the first thing to look at is this thing which I've highlighted in blue and red. By the way, this is in the outcard file, I must say. So the energy and the energy that's basically given out is given in red and blue. So you have something that looks like this. Check when this is written out in the previous step. It gives you a number, it gives you negative 42.17. And then you check what it was actually done. So VASP will then perform an SCF step after, and it will report what the actual energies are. As you may note, this number is particularly close to this. So your algorithm is on the right track. You predicted an energy, and that's kind of what it was. That's equivalent to saying that the green point that you predicted was pretty close to what the green point actually was. So you're in good shape if VASP is able to do this. That's the first thing to keep in mind. And if that isn't correct, then I would think a little bit about what's happening. The other thing to sort of keep in mind is the step that it's taking. This is particularly useful when you're deciding what totem is for some of the other methods. So make sure that you check what step is being used. You may also check and verify if this step is close to what's written as this step, the harm step or harmonic. If it's pretty close, this basically means that your potential energy surface is fairly harmonic to begin with. So it's a fairly simple system. It's basically what you can get out of this, or you're very close to the minima. This is of secondary importance, although it's called first order. It basically takes the product of the forces with the left force, the right force, and the mean force. Rather, I should say the mean force, the left force, and the right force with the energies, basically to sort of predict what the next first order change to the energy would be. So this is basically just a way of sort of determining how much the energy would change. And this is just an estimate of the same quantity. So this is stuff that you can see in the outcard. I think the most important thing to realize is basically if your energies are close to the next step energies. Everything else is kind of correlated to this. This is for the trial step. For the corrector step, you have the same thing. Again, you have what's reported as GAM. In the corrector step, this is basically just beta in the previous expressions that I showed, which keeps your directions orthogonal. So I guess the correct word for it is the conjugation parameter to the previous step. GFGS are the norm of the force and stress. And ORT, I guess, is the orthogonal, is to determine how orthogonal the different search directions are. Ideally, you want this number to be very small as compared to this and this. And if it is, it's making good progress. Your algorithm is going well because your search directions are truly orthogonal. And again, this is something to keep in mind for the other algorithms. You have this trial step. This is perhaps more useful than the previous quantity that I mentioned because this is in the steps of totem. So if you had a certain totem and you did this and you found it's like 0.946, this is kind of 1. So I would not change anything. But if it's much smaller or much larger, most likely going to be much smaller, I would think a little hard as to what to set totem for some of the other methods. Great, cool. So we've traversed quite a few algorithms now. We have steepest descent, we have dice, conjugate gradient. Now let's move over to perhaps the algorithm which is the simplest of the lot, maybe barring steepest descent, which is damped molecular dynamics. This is really simple to understand. It's like if you have balls in a well of some sort, or in a cubic lattice and so on, and they have some forces, you basically treat these balls as rolling balls with some force, and these balls are basically retarded with some friction, essentially. So this is as Newtonian mechanics as you can get. You have balls that are moving with some force, and then you try to retard them with some friction. So think of all of these atoms as just rolling balls with some force. Remember and recall that your second derivative of the positions, your acceleration, is proportional to the force. F is equal to ma in terms of Newtonian mechanics. It's kind of the same thing. And notice if you have a retarding force, it could be proportional to the velocity. That's how the friction in this particular case would work. And so your equation of motion for all of the different atoms would be the second derivative of the position, the force, essentially, or a factor of the force. So this is F is equal to ma with some factor. And this is basically just the friction that you have in your system. So you want to retard these rolling balls as they move towards the zero force position. And you just basically solve this equation of motion again and again and again until you reach a minimum. That's really it. So if you're familiar with molecular dynamics methods, this is much the same thing, just with some friction that prevents them from going all over the place. You want a relaxed structure at the very end. Algorithm is super simple. It takes in the positions. Note it takes in the velocities as well, and you'll see why in a moment. It takes in the energies, it takes in the forces, and it takes in the lattice vectors. So you have all of these quantities here. Wants to output out the positions. At first, again, you check if your forces have converged beyond a certain threshold. If you are at the first iteration, you set the velocity at that point minus a half step to 0. That looks like this. And then you perform, if you're not in the first iteration, you use the information from the half step that was before and the positions and the forces to determine the next velocity. So that's given here. And then you simply add that to the positions. This velocity is determined by the friction, which is given by mu, the velocity of the previous half step, which is given here, and your alpha, which is a parameter, much like the other alphas, which is just a scaling parameter, and your force. That's essentially what it's a function of. Some of you may be familiar with this as the Verlet algorithm for basically integrating velocities into positions. A half step is commonly used for these algorithms for many different reasons, but this is essentially what it's doing. You have positions, velocities, energies, forces, and lattice vectors. You get the new positions. These new positions are basically given as a sum of the old positions and the velocities that are determined at that half step. And then you basically sum them together and you get the new positions. That's pretty much it. How do you activate this within VASP? You set I prime as 3. You set portem to any value, which is alpha. You set your friction, which is given by S mass, so mu in this context. And as always, you have E diff G, which determines the threshold for convergence. That's how this basically goes. Caution and something to note. Well, before we do caution, let's look a little bit at its convergence. This is basically what it looks like. You have your position here as was defined before. And then this is your next position. So your velocity drives you in that direction. So something that looks like this. And then your velocity drives you in a direction from here to here. So these are the first 3 points, starting from this particular point here, which is basically driving you along a certain direction. So this is basically just the way the method goes. And it'll eventually, I'm sure, just make its way towards the minimum position. Again, simple function, illustrating this in a very simple way, just to sort of illustrate how the different methods work. So, okay, back to the caution. So note that choice of S mass and portem, so friction and step size is particularly important. I do this in an extreme example where I take a relatively simple system and just basically traverse the different step sizes from 0 to 1 and the different frictions from 0 to 2. And I illustrate how many steps it took to converge if it did. So why it blew up, it diverged. So it's the worst possible case. And basically what you see is you start off with something like S mass is maybe 0.4 or so is maybe where you reach the most success. And a portem, which is, you could go somewhat large, but then you take a large number of steps to converge, which is this green point. If you take very few steps, you get something that looks like this. If you take very, very large steps and with no friction at all, you may accidentally just reach the minimum. So that's kind of what's shown here. It's an interesting quirk of the system, but don't expect this to work always. I would say the best way to go about this is to start with a relatively conservative S mass like 0.4 and then change portem and then proceed forward with your relaxation. I would largely reserve this for systems where you have a very similar set of systems. I was studying, for example, metal oxides. or certain class of systems, and then you do this for one system, and then you kind of use it more broadly for other systems. It will work faster than methods if you know what you're doing with your parameters. Otherwise, you just may end up in this wide zone of divergence. So this is something to keep in mind. This is a cautionary note for this algorithm. Great. So we've done with all the algorithms now. We've done 4 of them. Last one being damp molecular dynamics, first one being steepest descent. I will now introduce a few caveats to our discussion, just to allow you to sort of understand how VASP works in general. So let's contextualize what we just learned. We have positions. So you have all of the different positions here for different atoms. So you have 4 atoms, 1, 2, 3, 4. You have all of their positions. VASP will compute their forces. You have 1, 2, 3, 4. You have all of the forces as vectors, and it will compute an energy. This is what VASP does. You take all of these different points and basically pass it on to what's essentially a black box optimizer, 1, 2, 3, depending on the I-prime that you choose. It generates a new set of positions. These positions are basically used, computed with DFT again in terms of the forces and the energies, and you go back and forth, back and forth, back and forth until you're converged. This is what VASP is doing, or what we've discussed so far. You could easily extend this to basically include not just positions, but lattice vectors. So your cell, and instead of your force, you get a stress. And then the algorithm is exactly the same. You just have to include these additional degrees of freedom. So lattice vectors and stress. So everything we discussed previously, you just tag along not just forces, you tag along the stresses, or the stress tensor, and you tag along the lattice vectors. It's a simple trivial extension to all of the algorithms that we discussed. How do you activate this within VASP? Well, there's one key, but there seem to be several options. There's ISIF 0, 1, 2, 3, 4, 5, 6, 7, 8. This is this nice mesh of things that you can change. You can do positions, you can do cell shape, you can do cell volume, up to you. And you can sort of decide which one you like. So for example, ISIF 3 is fairly common where you just switch everything on, switch on your positions, switch on your cell shape, switch on cell volume, and you get kind of a converged structure. Another thing that's popular may be not changing cell volume, but changing cell shape. This is also something to look at, but there are different options. All of them seem to be implemented. Give them a try depending on your certain application. So a combination of iBrian and ISIF. I've not mentioned all of the ISIF tags in the previous part of the lecture. I'm assuming this will be set independently based on the materials that you're interested in. So that's the first caveat. The second caveat is, say, for example, you don't really want to relax all of the atoms in your cell, or you don't want to relax certain atoms in your cell, or you don't want to relax certain atoms in your cell in certain directions. It's fairly easy to think about what you would do in implementing this. You would basically say, just switch off the forces on those particular atoms or in those particular directions. It's not terribly different from what VASP does internally. It's just, you just need to set selective dynamics in your postcard file when you're generating your postcard SO. And you get a list of positions. You can tag along what you want relaxed at the very end. So you can say true, true, false, for example, relaxes X, Y, Z. And false, false, false basically sets all other components of force to 0. So in this particular case, nitrogen generated this way will just not move. And that's all you need to set in your postcard file, and then you're good to go. So selectively relax things. There are reports, and this is something perhaps to verify that this helps with convergence. So removing a degree of freedom intuitively should help with convergence. This is particularly useful if you have a very complex system. And for example, say you have an adsorbate sitting on top of the surface. It may not always help to relax everything simultaneously. You may want to freeze a few things first, relax something, and then unfreeze. A good way to do it is through the postcard file, and that basically sets everything up. You could do the same thing for lattice vectors. This is an addendum to the previous caveat. You can do this just with an additional tag called lattice constraints, particularly useful for 2D materials where you don't want to basically change your z-axis. You don't want your surface normal axis to change, quite an irrelevant axis as long as you have enough vacuum. So you would basically set lattice constraints for this. What lattice constraints does is basically, say you set true, true, false. It takes in a Boolean of 3. You would basically switch off everything here and everything here. And this basically sets your stress tensor components here and here to 0. And then those lattice vectors just don't. And this is, as I mentioned, particularly useful for 2D materials where you don't really want one axis to change. And that's pretty much all you need. You're good to go in that context. And the final sort of summary of everything we've discussed so far in terms of the different I-brians. Let's look at a more practical scenario of what should happen. This is an example for the tetragonal phase of iridium oxide. I've made some color maps here for I-brian 1, which is RMM dice, I-brian 2, which is conjugate gradient, and I-brian 3, which is damped molecular dynamics. You have here C and A, which are the different lattice vectors. The positions are not represented on this figure, they're in the plane. The energies on this figure basically represent stable or unstable situations. The more darker blue you are, the more stable your energies are. The more yellow you are, the more unstable you are. So I start off all of the algorithms, I ran 1, 2, 3 with the different settings. So in this case, I set Potem and I let N3 be default, whatever VASP picks based on the eigenvalues. In iBrian 2, I only have Potem, so I set that as default. And for iBrian 3, I choose, just because I'm aware of the system, I choose a certain S mass and Potem. So I've done my due diligence. I know what the two parameters are, and I can basically pick them for the system. And what I get essentially is behavior that looks like this. So you can see that it's you starting here at 4.8 and 3, it jumps over here and then sort of goes around a little bit and then finds its optimal position. iBrian 2 jumps around a little bit more. As you said, it requires much fewer parameters to actually work. It jumps over, and then finally eventually finds its points. I must say the colors of the points indicate how many iterations it took to converge. So the more darker the red color is, largely implies that you have something which took longer to converge. So in this particular case, iBrian 2 just took longer, and iBrian 3, of course, converges much faster just because I know what the parameters are. So play around with the parameters for iBrian 1 and iBrian 2 if you're so inclined. iBrian 2 is mostly for things where you just want something that works in a very stable way. So a simple practical application, these maps sort of contextualize a little bit what the algorithms are about. So we've reached the second to last checkpoint of this presentation. We have our force and stress tensors. We can determine a pathway to a constant structure using some of the algorithms. There are 3 algorithms implemented in VASP. RMM dice, iBrian 1, choose Potem or N3 depending on your preference. Conjugate gradient, there's iBrian 2, choose a certain Potem, not much else you can do. Then there's damped molecular dynamics, choose iBrian 3, Potem and S mass, and you want to be careful in your choice here. And of course, choose ISIF to control cell volume, shape, and ion positions. We've looked through forces, stress, we've looked through density functional theory and how it helps you to get these quantities. And we've spent quite some time on relaxation algorithms. A few notes from some of us who have developed used a lot of these things, how this works. Take this as conventional wisdom. Of course, this doesn't apply everywhere, but this hopefully should get you started with some of the algorithms. It's not always going to be the case, but I think it's a good start. I think a common question that we've all asked ourselves or heard from others is basically, what algorithm should I use? So which one should I pick? There's been several bar charts of these floating around in different eras. I try to contextualize it for our era. If you're studying a variety of systems, if you're doing high throughput calculations, I would stick to conjugate gradient as a first step, maybe not do a whole lot. If you are not, and if you're close to the minima, say for example, you are starting from an available structure, you start from an experimental structure, maybe something where you took something off the internet of a certain database, you're fairly close to the minima to begin with. Then, and if you have not that many atoms, you just also pass it to conjugate gradient, don't worry about it, it just works. If not, so if you have large number of atoms and you have an intermediate number of degrees of freedom, so something which is less than 20, pass it to RMM dice, it should just work fairly easily. If not, say for example, you have very many degrees of freedom, it's a huge system, simply pass it to damped molecular dynamics. The same case applies if you have something which is not particularly close to minimum. Maybe you generated a structure by hand, damped MD is the way to go. If you are again not bothered to tune the parameters, just go back to conjugate gradient. This would be significantly better than damped MD. So hopefully this contextualizes what you should use. It's fairly heuristic, and I think the sort of general vibe is start with conjugate gradient, but this is something to play around with. The next, perhaps a little bit more philosophical thing is, when can I say something is converged? This is something that you have seen already at the start of this presentation, and let's set this a bit in stone. Say, for example, you have a potential surface and you're somewhere here, right? So you're already getting close to convergence and you want to see when you can stop. The first check will be to see if the energy doesn't change. So for example, if the energy doesn't change, you're probably very close by. So if you're here, for example, you take another step here, the energy has changed a lot. So you're probably not converged. But if you're here and you change a little bit here, you're probably converged because the energy doesn't change. It's not a foolproof check, but it's a check nonetheless. You would do this by setting a positive number to E diff G. that's basically given here. You could also basically do a slightly more rigorous check, which is the forces, which is just the energy gradients, and make sure that they're close to zero. In this particular case, this would mean that your forces are zero, so which is a good test for convergence. So your forces here are basically zero. Your forces here are definitely non-zero. This is done in VASP by supplying a negative number to E diff G. So be reminded that this negative number doesn't mean it's a negative force. It basically just means that it will decipher this number as being a force criteria. And so you would set the normal forces need to be lower than 0.02. And that's what you're seeing here. The more rigorous test, if you're really looking for something very stable, is to check if the curvature of the system is positive. So you would have to do what's called an I-Bryan is equal to 5 calculation to compute these phonon frequencies and check whether none of them are imaginary. These are the 3 different criteria essentially to check whether something is converged. I tend to, for at least some of the stuff I do, is basically keep this criteria as the default and check with force criteria. There are cases, of course, where you require something more stringent. There are also cases where this is perhaps too stringent and you can get away with energy convergence. So I've not come across a whole lot of those. So the default usually is just to set force convergence and hope for a converged force in your system. This would be the default way of working, at least for some of us. And just a caveat to sort of visualize some of these things, I've collected a few of the different issues that we've seen in the past. I think a large chunk of them are basically your atoms are too close to each other. I highly recommend viewing structures before running DFT on them. So, for example, VASP has a simple utility where you import the calculation and then you just plot it, pop up a window and it'll plot what you have. You can also check if you have reached convergence in all your ionic steps. So you reached SCF convergence in all your ionic steps. Simply import VASP and then do calculation.ossicar.is converged, and it will tell you whether your electronic steps have converged along the way. Sometimes if you don't have a converged electronic step, your forces are awful and you basically go in a different direction. This is what this is telling you. You can, of course, try another I-Bryans if you're using 1 and 3, perhaps switch to 2 would be a good go. And make sure that your basis set is not too small, just increase the n count if that's the case. And a couple of final notes. Please be aware that the significant digits that you require in your postcard file, the requirements are not 0. So make sure that, for example, you had an atom position that looked like this, you would be inclined perhaps to set 0, 0, 0, and 0.25, 0.25, 0.25. Highly recommend basically having the right number of significant digits in your postcard file. Also recommend a very nice library from SPGlib to basically symmetrize your structure. This does help. If none of these work, there's a tag in VASP called Simprec. I highly recommend looking it up on our wiki to see what it means. It essentially, at a very surface level, it determines the tolerance of the symmetry operations that VASP uses. Do give it a check and see whether it applies to your system. But I think the easy way and the most no-brainer way to go would be to symmetrize or set the number of structures or set the number of decimal places to the right number if that's what you're interested in. Another thing to sort of mention is that if you have sort of jagged plots in energy versus cell vector, so you're doing relaxations and you get some points that look like this, or you're not, this is of course a cubic fit, but you're not really able to fit a nice equation of state. I think a good indication of this is so-called Poulet stress, which is to say that you don't really have convergence in terms of the basis set that you've chosen, so your basis is too small. I would largely increase your basis to 1.3 times the default DN cut. This seems to be the standard way of doing it. It also seems to work in a lot of cases, so this would be the first thing to try. Another thing to sort of mention is that if you're after very, very accurate energies, please do consider running a static calculation with NSW0 with the concard generated after relaxation. This helps. There's a lot of documentation about this on our wiki. I highly recommend taking a look as we go along. There's a lot more information, a lot more examples, but I think these are a couple of caveats that I thought I'd mention, perhaps out of context, but something that you could stumble upon very quickly. And finally, of course, something which is we have not spoken about in this presentation is that you tend to fall into not just one local minima, but several local minima with these methods, right? So say you start from here, there is no guarantee that you fall into this nice low energy structure minima. You could basically descend down this pathway and go here. This is perhaps not ideal. Maybe you're not looking for this and so on. So I would basically go with an approach where I try several different cases. This is something to discuss, the open-ended research problem as to how to to convincingly go towards a global minima. But all the algorithms we discussed so far will basically take you towards a minima. It may not take you towards the global minima. It's a common issue in all of the common relaxation algorithms. I will, as a very last step, illustrate a few of the community tools. These are by no means exhaustive. I would say they're far from exhaustive, but these are tools that I have worked with in the past and hence recommend. So there are a few different tools here. I flashed them on the screen, whether they're about structure manipulation, databases from which you take structures from, relaxation tools, high throughput tools, and so on, and of course visualization. So I highly recommend taking a look at these. These are fantastic. And play a great role in developing material science. So do take a look. They're basically great. So this brings us towards the end. What quantities do we need? We need the force and stress tensor. How do we get these quantities? DFT, VASP in particular, is great. Relaxation algorithms get us a long way from high energy structures to stable structures. Calculations, when converged, you could do this through energies, forces, eigenvalues of the Hessian. We discussed a little bit how to proceed if a calculation does not converge, but this is trial and error. Our wiki is a great source of information for a lot of these things. Symmetry consideration is quite important, and insufficient basis size also particularly important. And yes, I guess with that, I'm through. I hope you got a clear understanding of what forces are, stresses are, and how they are used in structural relaxation. And with that, I'd like to close.
Thank you, Sudarshan, for the comprehensive introduction into how the different algorithms for structure optimization work in VASP, and also with some practical advice how users can then choose which method to do and what parameters they can tweak in the input files.